Let's talk about multiple hypothesis testing. What is it and when do you need it? Suppose you're an experimenter and you have some data set and you have a long list of possible things that data set might be informative about. So you take the first thing and you invent a p-value test that will be relevant to that. That is to say, you think of a null hypothesis and you see whether your data can rule out that null hypothesis. And you get a p-value, and suppose that p-value is not particularly significant. So you now go on to your next hypothesis. And that gives a p-value, and maybe that one is not significant either. And then you go on to a third hypothesis. Well, if you think about this, you'll see that sooner or later you're going to get a small p-value just by chance, even if the null hypotheses are not ruled out. In other words, if the critical region, the region in which you will call a p-value significant, is, say, 5%, then after you've done about 20 tests, you'll get one in that 5% critical region, whether your hypotheses can actually be ruled out or not. So we have to make a correction to reduce the significance level of any one statistical test when we know that we're going to try many such tests. And that's called multiple hypothesis correction. The standard way that this correction is done is what's called the Bonferroni correction. Here's Bonferroni, whose years were 1892 to 1960. This is a very conservative test. It's the gold standard. If your data passes the Bonferroni correction, then your data really is significant. It's so conservative, however, that sometimes you're going to lose valid discoveries by using the Bonferroni test, and we'll talk about that a little bit later. The idea of the Bonferroni test is to calculate the probability that one or more of the n tests will accidentally fall in their critical region. So if alpha prime is the critical region that we naively think we're starting with, so alpha prime might be 5%, then we can calculate the probability that one or more tests will fall in their critical region, and we're going to call that alpha. And let's see what that is. That is the probability that all of the tests did not fall in their critical region. So that's 1 minus alpha prime to the nth power. And then we have to subtract that from 1 to find the probability that one or more tests will fall in the critical region. Now we're always interested in pretty small values of both alpha prime and, as we'll see, alpha. So in general, one can make the binomial expansion of this term, and we get, therefore, that it's 1 minus n times alpha prime, and the 1 cancels the 1, and we get over here n times alpha prime. And what have we learned in this approximation? We've learned that if we called a 5% critical region as being the interesting one, and we do, let me make up an example, 3 multiple hypotheses, then the actual critical region we're looking at is 15%, which is not what we want at all. So in fact, the way you do this is you set alpha to be what you really want your significance level to be, so that alpha is equal to 5%, and then you'll see that alpha prime, the significance level, the p-value that you have to require on each test, is n times smaller than that. So for example, if you want a genuine critical region of 5% and you're going to try 10 hypotheses, then on each one you must set a critical region of 0.5%. Now you can see that in our calculation here that we assumed that all of the tests were independent. That's what gave rise to this power n up here. In practice, that's rarely true, and this is what makes Bonferroni the most conservative of all possible tests. To see that that's the way it works, let's consider the opposite extreme. Let's suppose that we repeat the same test n times on the same data. That would be a pretty silly thing for a single person to do, but I guess you could imagine that we have n non-commuting graduate students in separate rooms. They don't talk to each other. They each open the same statistics book and they try the same test. Well, in this case, you can see that alpha and alpha prime are the same. A test doesn't become less significant if we repeat the same test multiple times as our multiple hypotheses. This may seem a little bit fanciful, but it's the other bounding case, and the truth is always somewhere in between. Different statistical tests on the same data set are not completely independent, but nor are they completely dependent if they're not the same test. So slavish adherence to Bonferroni, because it's so conservative, is in some ways a curse on biomedical research. Nevertheless, it's the gold standard. Why is that? Because it's much better to be overly conservative than to have a biomedical literature that's full of wrong results, and results can easily be wrong if each experimenter is allowed to try test after test after test, fishing for statistical significance until they get the appearance of statistical significance just by chance on one test. But there are alternatives to Bonferroni that can be used in many cases. We'll now talk about one that's called false discovery rate, or FDR. False discovery rate, as I just said, is a good alternative to Bonferroni when the latter is too conservative. Now, you can't apply false discovery rate to all situations, but here's the situation that it does apply to. Suppose that you have 1,000 drugs and you're going to test each of them in a clinical trial to see if it significantly helps the patient. So in each of these trials, you get a p-value, and a small p-value would indicate a statistically significantly good drug. Or another example might be that we're going to test whether genes are relevant to disease, and we're going to do a test on 10,000 genes. Now, in the null hypothesis that none of these drugs are any good, or none of these genes are implicated in disease, then the p-values that we get will be uniformly distributed because they're simply p-values drawn from a succession of null hypotheses. So I've drawn a picture down here where I've showed as a function of what the p-value is between 0 and 1, how many times out of the 1,000 or 10,000 we get a p-value of that amount. And it's a little square wave here because I've broken them into bins and plotted a histogram of how the p-values occur. Well, if the p-values really do look uniform all the way between 0 and 1, then we haven't discovered anything. But if there are things there to be discovered, then we may find an excess of small p-values. Now, do all of these small p-values represent true discoveries? Not at all, because we can see here that if this is the rate of uniform p-values for false discoveries, we should extrapolate that in. And even when the p-values have an excess at small values, this pink region here is going to be correspond to a set of false discoveries, whereas this green region, the excess over that, is going to be true discoveries. So we can see that they're there, but of course we don't know which p-value within this bin, for example, is in the pink and which one is in the green. So the way you frame false discovery rate is you say, how small should I make this p-value so that in the range to the left of that, the ratio of green to pink is acceptably large. That is, some of the discoveries are going to be false, but I want to control the fraction of those false discoveries to some value. For example, we're going to call it alpha, to some value, for example, alpha equals 5%. Now, the way I've drawn it here, it looks like I have to kind of fit a model. I have to kind of extrapolate this flat curve in and then actually construct the green and pink regions and then walk my way up until I get the acceptable ratio, 5%, which, by the way, in this picture it looks like I never achieve. The interesting discovery by Benjamini and Hochberg is that there's a principled way of doing this. The way you do this is you take all the p-values that you've been given, and instead of binning them into a histogram, as I showed you on the previous page, you rank them. So if there are m p-values, you rank them from 1 to m, and then you plot the curve of what the value of the p-value is as a function of its rank. So there are m little steps here. And of course, the p-values are between 0 and 1, so we have 0 on the vertical axis here and 1 on the vertical axis here. Now, if the p-values really were uniform, then we would simply be looking at the rank of uniform random numbers, and that, there might be some statistical deviations, would basically go up a 45-degree diagonal. So the fact that we have some true discoveries here is indicated by the fact that this curve goes over at a small slope before going up to a large slope. And in fact, an idealized version of this curve we can draw over here. In this curve, we've assumed that there is some fraction of the p-values are very, very small, so that on this picture they look like 0. And then after we've exhausted them in the ranks, the remaining ones are random between 0 and 1, and so they'll basically climb up a linear curve going up to 1 here. Now, the prescription of false discovery rate, shown here, is that if you want to set a limit on your fraction of false discoveries alpha, then you should take as real events all events that have a p of k less than a value k alpha over m. Geometrically, what that construction says here is that there's a red line of slope alpha, because it goes when k is equal to m, we get the vertical height here alpha, and it's linear in k, so it goes linearly up this slope here. And the intersection between our p of k curve, which was this black curve, and the red curve is the critical value of pk, below which we should call the discovery real, above which we should ignore the discovery. So this is pretty amazing and maybe a little bit unintuitive, but let's see why geometrically it works out. And we're going to do the proof only in this idealized version, and you'll be able to figure it out. So first we have to compute what is the location of this intersection point, and in this graph I'm calling it x0, y0. Okay, and the intersection point has to be the point that's satisfied by both of these curves. Now, the red curve says that the y value here, y0, must be equal to alpha, the slope, times x0, the distance here. So that's the left-hand side here. And the black curve says that if we subtract off this fraction f, which are the true discoveries, so that's x0 minus f, okay, then we go up this slope here, which is a slope of 1 over 1 minus f. Why? Because it goes up 1 in a distance of 1 minus f here. So x0 minus f times the slope should equal the same ordinate y0 as we got over here. So we can solve this for x0 in terms of f, and I've shown that here. Now, what's the false discovery rate? What fraction of the events that we're going to call as real are actually not real? Well, in the graph you can see that from 0 to f here are the real events, and the events that we're going to call as real are from 0 to x0 up here, a value that we just computed. So the false events are the ones that lie in this little interval at the bottom of this little triangle right here. And their fraction of all of the events that we're going to call is therefore x0 minus f, that's the little segment here, divided by the full x0, that's the full segment here. We have a formula for x0, and if you substitute that into this expression for false discovery rate and do a little arithmetic, it comes out exactly alpha times 1 minus f. And f is a positive number, so this is always less than alpha. And what have we learned? We've learned that if you do this prescription, your false discovery rate is guaranteed to be less than the threshold alpha that you've chosen in advance, perhaps a number like 5%. There are fancier proofs for the non-idealized version where we don't assume that the curves are straight lines over here, and I'll leave it to you to look those up in the literature. Okay, that's actually all we're going to do with p-values and multiple hypothesis testing for right now. But before I let you go, I want to go back and give us a Bayesian gloss on what we've just been doing. Bayesians have a much easier time with multiple hypothesis correction than frequentists do, and I want to show you why here. Of course, to be able to apply Bayes at all, we have to be in the happy case that we have an exhaustive and mutually exclusive set of hypotheses. So we can't just have an open-ended, well, maybe this is a hypothesis, oh, maybe this one, oh, maybe I think of a third one. We have to be able to write down in advance what all of the hypotheses are. So let me do an example, and you'll see how this all works out. Suppose we think that a particular kind of cancer is caused by either one or a combination of single nucleotide polymorphisms, or SNPs. These are individual mutations in the genome. So our experiment is going to be, we take a bunch of patients and we genotype each patient. That is to say, in each patient we measure all n SNPs. And to make the example simple, suppose that each SNP has two possible outcomes, two alleles. And we want to see, are there any patterns in this that will explain the cancer? Notice that the number of hypotheses is so large that if we tried to do a Bonferroni correction on this, we would never be able to get enough significance. Because if n is even as large as 20, then 2 to the 20 is 1,000,000, and we can't possibly get a significance level less than 5% divided by 1,000,000. But we're Bayesians and we think about this differently. We're actually saved by a prior on the hypotheses. All of these hypotheses, all 2 to the n of them, have prior probabilities, which of course must add up to 1. Now, quite typically, our prior on models like this is that we really expect that many cancers are caused by one SNP. So when I say really expect, perhaps a quarter of the time we think is a prior probability that the cancer is going to be associated with one SNP. So in our outcome space here, I've carved out a region that's maybe a quarter of the outcome space. And all of the one SNP, the 20 hypotheses, populate that region of the outcome space. Then we think if the cancer is not caused by one SNP, maybe it's caused by two SNPs, and maybe there's another quarter of the outcome space that we partition up into all the hypotheses that vary by two SNPs. There are a half times n minus 1 of those, namely the number of ways we can choose two SNPs out of n. And you'll notice that the prior probability for any one of these hypotheses, for example this one here, is in general much smaller than the prior probability of one of these up here, because there are more of them to fit into the same 1/4 of the outcome space. And then if the cancer isn't explained by two SNPs, we think it might be explained by three SNPs, but there we're assigning, let's see, what does it look like? It looks like maybe a 15% probability as our prior on that. And then that's divided up into on the order of n cubed possible hypotheses, and so on for 4 or more greater SNPs. Now we just do the Bayes thing on the data. And we ask if the evidence factor is sufficiently great to overcome, for example, in the case of a 3 SNP model, this relatively small prior probability for the model. That's all we have to do. There's no multiple hypothesis correction. The multiple hypotheses, because they're EME, and because we've put priors that add up to 1, basically just all take care of themselves. And that's a great thing about doing this kind of analysis in a Bayesian way.